Let me press it. And let's see if it works. Okay. So I think it is recording right now. So once more, let me just deal with the technology. It's a pleasure to be here. My name is Pawel Dlotko, and thank you very much for the introduction. And today I would like to invite you to applied and computational topology. And by doing so, well, in order to achieve it, I would like to give you some background about the topic. So essentially, there are two main working courses of topological data analysis. One of them is a persistent homology, and another is mapper algorithm. We'll discuss briefly both of them. Again, we won't be able to get in any depth into mathematical details, but I'll try to highlight some of the issues, some of the problems we have over there. And again, the main philosophy of applied and computational topology or topological data analysis is to be able to use mathematics outside mathematics for benefits of other fields. And therefore, I'll show you a number of examples where actually that thing happens. Speaking about the credo of topological data analysis, applied topology communities, the data have shape, shape has meaning, and meaning brings value. And I think, the quote is coming from Gunnar Carlson. It may sound a little awkward at the beginning, but let me just tell you that we all saw an example of the fact that data have shape and shape has meaning. If we have some observations in which we see a linear trend, and this trend we can find the parameterization of this trend by doing a very simple linear regression. And the fact that we can do a linear regression is really because the data happen to have a linear shape. Obviously, they are not perfectly linear, and that's something which is quite common in the real data sets. There is always certain amount of noise, sometimes less, sometimes more, and it's always creating a lot of problems. But well, this is how it is, and in this work we need to deal with it. And, the fact that this data have a linear shape allows us to build an algebraic model in the form of an equation y equals ax plus b that describes reasonably well this data set. Problem is that most of the data in nature don't want to be linear. So we may have a periodic behavior, in which case the data will be moving around some cyclic trajectory, quite often in high-dimensional space, maybe a trajectory in the shape of a figure 8, for instance, if we sample Lorentz attractor, that's what we would encounter. And that there is a very large variety of shapes our data may take a form of. And oftentimes, we don't have a luxury of being able to visualize our data in two-dimensional space. Therefore, well, if we try to go ahead and use an algebraic model, try to fit an algebraic model into the unknown data, quite likely we will overfit, and the model simply won't fit the data. And moreover, well, except from looking at the root mean square error, we will not be able to detect it. So what we are trying to do in topological data analysis, instead of trying and enforce a certain model, well, we are trying to build a model directly based on the data without assuming whether this is, something cyclic, figure 8, or maybe one of those y-x junctions, or anything similar to this. Okay. So in other words, we really want the data to determine the model rather than us trying to guess the model for the data. And looking at the topological data analysis, as I mentioned, we have a persistent homology, and I will briefly introduce it at the beginning. We have these accurate network models to maybe not examine, but to summarize landscapes of the data. We will be speaking about the mapper algorithms. The kind of a selling point for those techniques is they are stable in a certain sense. So small perturbation of the input data won't change our representation that much. They're fully explainable, so there are no black boxes. And what do I mean by that? Well, if you have ever encountered um, machine learning, deep learning, neural networks, they are considered to be black boxes because they just give an answer without providing an explanation how the answer was obtained. And again, we are trying not to enforce any model. Instead, we are trying to build the models of the data and make some inference based on it. And by the way, if you happen to have any questions, please feel free to interrupt me at any moment. I would very much like to have some questions. And in fact, I'm having one question for you right now. And I know it's a tricky question, but if you could try to answer and tell me, what do you see in this slide? And there is no good answer, there is no bad answer to this question. It is a sociological experiment, let's put it like this.
A ribbon.
A ribbon.
Circle.
A circle. Say again? The last
Pet.
pet. Okay. Again, as I told you, there is no good or bad answer to the question. However, taken three answers. One was ribbon and one was circle. And well, speaking about ribbon, it is topologically equivalent to a circle. So the majority vote goes for a circle. And well, I can be the devil's advocate and say, well, there are only 19 points in a plane. But I think we can make the statement about circle a little bit more precise by saying that if those points are sampled from some probability distribution, then this probability distribution is perhaps supported close to a circle. And persistent homology is a tool to make this observation to really say, okay, we are seeing a circle over here, a little bit more precise. So what I can do to actually see a circle instead of 19 points, well, I can put a balls of a certain radius r and put one ball for centered at every point. And now what I can see is really a ribbon which can be retracted to a circle. And that's kind of a good news. Question is, how do I choose the radius r? Because, well, I can make this experiment on the plane. In the higher dimensions, it won't be possible. And what we are doing in persistent homology is we are not choosing the radius r. We just place a ball of a radius r centered in every ball at every point from this initial collection of points, and we let r grow from 0 to infinity. So we have this nested collection of spaces or a filtration, and this filtration will give us a filtered simplicial complex. We will get to filtered simplicial complexes in a second, right? But the long story short is, if we really think about this circle, there is this hole in the middle, and this hole is present for large continuous collection of radii, and only for very large radii we don't see the hole anymore. Okay, so what I want to do right now is to look at this space, which is large, continuous, infinite space, and build a finite combinatorial representation so that I can put this representation on my computer and actually do a calculation. And at the end of this calculation, I want to be able to say that there is really a circle over there. So how do I do it? Well, let me introduce to you first the combinatorial structure, which is used to store this information. And this basic combinatorial structure is this abstract simplicial complex. So what is an abstract simplicial complex? Well, it is a collection of sets, script K, such that for every set from this collection, if I take any set from this collection, and every subset of this set, then this subset have to belong to a collection. In other words, the script K is an abstract simplicial complex if it's a family of sets closed under operation of taking a subset. Okay, So that's an abstract simplicial complex. Think about this as mathematical data structure that we will use. Now, we have a point cloud P. This is a finite collection of points, and I'm able to measure a distance between them. Now, in what follows below, I really want those points to live in Rn for some n, but in the whole generality, we can only think about discrete metric spaces if we wish. So there are a number of ways we can get from points to abstract simplicial complexes, and then to homology, and eventually to persistent homology. One of them is so-called Rips complex construction. So I'll say that a collection of points, P0 to Pn, um, forms a simplex, forms an n-dimensional simplex. If I take an intersection of a ball centered in Pi and the ball centered in Pj for I and j between 0 and n, and both balls have the radius of epsilon over 2. Epsilon is my parameter. Well, if those balls have non-empty intersection, no matter which Pi and Pj I choose, then this collection of points, P0 to Pn, support an n-dimensional simplex. So what I am doing over here is to check only the pairwise intersection. There is, let me say, a more ambitious version of this complex, which is called a check complex or the nerve complex at the level epsilon, in which, well, I require that all the balls centered at all those points, P0 to Pn, with the radius epsilon over 2, they all together have non-empty intersection. And then, and only then, I place a simplex of dimension n in the check complex, right? So please note that, well, that's a stronger condition. So if we have this condition, we have a simplex in a check complex, then we have a simplex in the Rips complex for sure, but not vice versa. And there are certain consequences of this. But before I move to the consequences, let me actually draw 4 points. And for epsilon equals 0, the balls will none two balls centered in different points will have non-empty intersections. So we'll just see 4 vertices. If we allow our epsilon to be a bit larger, meaning just a bit more than half of the distance between those 2 points, then we'll have one-dimensional simplex, one edge. If we allow to increase our epsilon so that the longest edge, the half of the length to the epsilon equal to the half of the length of the longest edges among those 2, then we'll have all the 3 edges in this simplex, but also we'll have a triangle, we'll have a 2-dimensional simplex. And again, this is because, well, if we want to input a higher dimensional simplex, well, this condition directly translates into a statement that, well, we put 2 or 3 or higher dimensional simplex if all the edges, all the one-dimensional elements in the boundary of that simplex are present. So at the moment we have all 3 edges supporting the triangle, we input a triangle. Now, if we allow increase our epsilon a bit further, perhaps we'll be joining those 2 points with an edge, because our epsilon will be just a little bit more than half of the length of that edge. Likewise over here, but again, the moment we add the last edge, closing up this triangle, we also add a triangle. And if we would have tetrahedra, then of course the same statement holds. So Rips complex is the most common complex used in topological data analysis for a couple of reasons. First of all, it's easy to compute. Secondly, well, it only requires information between distance of pairs of points. So we can construct it for arbitrary finite matrix spaces without actually caring if it is embedded into, if this metric space can or cannot be embedded into some Euclidean space. So you can build Rips complex essentially for anything. In fact, you can push it even further. D do not have to be a metric. It can be a similarity measure, so we don't really care about triangle inequality. etc., etc. So it's easy, but there is a price to pay. And the price is, well, if we look at the sum of the union of balls centering the points of the radius epsilon over 2, we can ask if the Rips complex is equivalent in terms of homotopy um, to the union of balls. And this is not the case, because if we have a situation like this,
Can you
where,
speak a little louder?
oh yes, sorry about that. I'll try to speak up. Is it better?
It's okay now.
Okay. So if we have 3 points like those ones over here, and if we put balls of a radius epsilon over 2 such that every pair of balls have non-empty intersection, then the Rips complex of this configuration will be just a two-simplex with 3 boundary edges and 3 boundary vertices. However, the union of balls is homotopy equivalent to S1 because there is a hole in the middle. And this is something which will not be captured by the Rips complex. It will be, however, captured by the Czech complex. So that's why if we want to actually accurately capture this type of small holes, then we should move to a Czech complex construction, which is, again, possible to make in Euclidean spaces. And again, that's the situation over here. So Czech complex is really coming from a mathematician named Czech who actually proven the nerve theorem in early 20th century, which state that this Czech complex is homotopy equivalent to the union of the balls. So we have a complex which is nice from a perspective of topology. It is a bit more difficult to construct, and again we kind of have this assumption of our point cloud P being embedded into Euclidean space. So there is a price to pay, but of course we gain something. And I'd like to mention certain problems. So if you ever did any computations, or if you ever will do any computations in topological data analysis, quite likely you will have to restart your computers because you will run out of memory. And why is that? Well, let me give you a reason. So suppose we have a collection of points, like the one presented over here. And if I'm not careful enough in choosing the epsilon parameter, which is twice the radius of the balls, then it may happen that I will choose an epsilon close to the diameter of the point cloud, right? Well, what will happen over there? Well, in that case, we'll have n choose 1 vertices, that's okay. But then every pair of points will be connected by an edge. So we'll have n choose 2 edges. And then every triple of points will constitute a triangle. We'll have n choose 3 triangles. And well, if we build our Rips complex or Czech complex up to a high dimension, and obviously, we have the sum of binomial coefficients, which became factorial and therefore exponential with respect to the n. And exponential memory complexity is a bad thing, but again, this is something we are encountering quite often. There are again ways around it, but that's a standard way. So quite often, the combinatorial representation, even though it's finite, it may be of an exponential size with respect to the input size, which is the size of the collection of points. That makes some of the computations harder. And I think I should mention, so there is a way of going around this problem. So if you look at that picture, well, the reason why we are getting this combinatorial explosion, this n choose 1 vertices, n choose 2 edges, n choose 3 triangles in general, n choose k k minus 1 simplices, is because we allowed connection from every point to every other point. So if we want to avoid this problem, what we need to do is somehow to restrict the connections only to from any point, only to its local neighborhood. And there is a way to do this, which is hidden under the big name of alpha complexes. But the whole idea is very simple. We take an idea from a computational geometry, which is the Voronoi diagram. The Voronoi diagram is for a collection of points. It's just a decomposition of a space into regions, and the points in every of those regions have a property that the point, this point over here, is the closest among the points from my point cloud, right? So in other words, the formal definition would be that for a given point cloud P, we divide a region, we divide the space into a collection of region, and every region, for points in every region, there is a unique closest point from my point cloud. This way we get this decomposition, which is called the Voronoi diagram. It's quite straightforward to prove that Voronoi cells, which are the cells corresponding to the points which we have over here, they are convex. And now, if we go back to the nerve theorem by Czech, then we would realize that we really don't need to intersect balls. We may as well intersect convex objects. Now, if we take Voronoi cells, intersect them with balls, we intersect two convex bodies, we get something convex again. So based on those intersections, we still get, we can still use the nerve theorem. So we still have a preservation of the homotopy type. But because Voronoi cells of the points which are far away, they don't have empty intersection. Because of that, we'll never have an edge, for instance, between this point and that point. So intersecting with Voronoi cells allow us to enforce some locality on the structure. And well, that's how we can remove some of the computational issues. But again, only some of them, because complexity of obtaining combinatorial representation of a Voronoi diagram also grows exponentially with a dimension. So there's still a lot to do. But that's a big topic about how to turn a point cloud into a simplicial complex. And it could be a topic for a long seminar or more. But I don't want to stay over here for too long, because I really want to give you a proper invitation to apply topology. So simplicial complex is, whichever we take, RIPS, Czech, alpha complex, is just the beginning of the way. Then what we want to do, we want to define chains, cycles, boundaries, and eventually compute homology group, and eventually later on compute persistent homology group based on the simplicial complex. And I'll just carry on and bring you over there. Okay. And here's another problem. So I will not be defining homology formally because there is not enough time. Let me just say that, that there are those main concepts, which are chains, cycles, and boundaries. And let me kind of hand wavy, although you cannot see me waving my hands right now, explain what are the chains, cycles, and boundaries. So a chain is just a collection of simplices of a fixed dimension with say, integer coefficients, right? So I can take this edge with coefficient 2, that edge with coefficient 5, and that's a chain. Cycles, on the other hand, they are chains that have an empty boundary. And they really are in agreement with the cycles we know from a graph theory. So a cycle is a collection of, in this case, for instance, it can be a collection of edges that have an empty boundary, right? So you need to really close up together. But it can also be a figure eight thing, right? So if I take a figure eight, like I take those 4 edges plus those 4 edges, that is also a cycle. And now, once we have a cycles, then kind of we can realize that, the cycle that goes around the central hole and this cycle over here, and I hope you can see my mouse pointer right now, they're kind of different because this cycle, it can be composed by boundaries of this, that, and that two-dimensional simplices, right? So if I actually take the boundaries of this, that, and that simplex, I'll get this cycle. And I cannot do it for the central cycle. So they are different. And the real difference is that this cycle over here is a boundary of a collection of higher dimensional simplices, which I just named, and this one is not. And the whole purpose of homology groups is to discover cycles which are not boundaries because they are somehow important. The cycle that is not a boundary tells us that there is a hole, and if we know that the cycle is formed from one-dimensional simplices, we know that this is a one-dimensional hole in our space. That's precisely the cycle we started from. And well, that is a conclusion which we can get by looking at some algebraic machinery. Again, I do apologize for not being any more detailed, but it's simply not possible to give a general and at the same time formal introduction in 1 hour. I will be more than happy to point you into appropriate resources or talk to you later about all the formalities. Okay. So now, up till now, I was speaking about very standard homology theory, but let me kind of go back to this process which we saw at the beginning when we fixed the radius of a ball and we let this radius, we didn't fix it, we let it grow from 0 to infinity. And when the radius of ball grows from 0 to infinity, then new simplices in our Ripps check or alpha complex are appearing. And what I want to do is to write them down in order of their appearance. This order, this sequence of simplices, I'll call the filtration. And suppose that we don't go all the way to infinity. We just stop the growing process for some epsilon, say equals 3, 14, 15. And we see what are the simplices over there. What we can do is to use an algorithm, which is essentially a Gaussian elimination algorithm to compute homology group. And we will get a homology of that complex restricted to certain epsilon. But then, once we will start adding new simplices, then we can kind of carry on this computation and get an information about how homology is changing as we are adding more and more elements or simplices of a larger radii. Well, and then once we actually do this, we can see how the homology groups are evolving. We can see some of them forming. For instance, in the illustration we started from, we saw a cycle forming for some small radius of balls. Eventually, for very large radius of balls, this cycle will disappear. And if you carefully track what is happening as you are doing the Gaussian elimination, you will be able to tell which cycles represents the homology groups being created, which cycles which elements of our matrix represents the cycles being destroyed. And that's precisely the information which we get from persistent homology. So we know when certain cycle is created, we know when certain cycle became topologically trivial, or in other words, became a boundary. Again, I do apologize for not being more precise, and I will be happy to do a follow-up on making the definition much more precise. But if you want to keep it on a general level, I will just say that persistent homology is a rigorous way of quantified closed shapes. So it tells us about connected components, and it tells us about the cycles, and this is what we saw in the examples. If we include higher dimensional simplices, it will tell us about the voids, for instance, like the one inside the ball, and we can really push it to higher dimension. What's nice about it is that we don't care about the ambient dimension. Our point cloud may live in two-dimensional space, as we saw in the illustrations. It can live in a few millions dimensional space, and the computations are exactly the same. Homology is also invariant with respect to the large family of deformation, rotation, scratching, mirror imaging, etc., etc., and that also will turn out to be important very, very soon. Not only that, so here's another kind of question for which there is no good answer. Um, Again, if we see an image like this, I can ask, well, do you see a lot of B's and or a single A? And obviously, we can see both depending on which level of details you are looking at. Well, if we are looking at the close distance, we see a lot of B's, but if we move far away, perhaps we won't be able to see the coarse detail. We'll be able to see the large letter A. Again, this is not very geometrical, so let me give you a more geometrical example. So if we have a cycle, a big cycle over here, composed of a collection of small cycles, uh, again, do we see a lot of small cycles or a big one? Again, the answer to this question depends on the resolution on which we are looking at the data. And persistent homology will precisely tell us that if we look at the high resolution, we care about small details. There will be a large number of cycles of a small radii. But if we let our epsilon grow, then those cycles will trivialize in terms of homology, and we'll see one big cycle going along this loop. And kind of one single word way of summarizing what I'm saying is that persistent homology is a multi-scale invariance. So it really tells you what is happening in your data set in the different scales. Okay, so that's all good. There is one more property, which is very important, that makes this thing useful in data science. So as I mentioned, all the data are essentially coming with noise. If you have noiseless data, that's extremely, extremely rare. And let me just give you a toy example. So what I have on the left is just a collection of points sampled uniformly from S1, from a unit circle. So that's over here. If we move right here, it's the same collection of points, but with an additional uniform noise of a certain amplitude. And likewise over here, I just increase the amplitude of noise. And for each of them, I actually did this construction. So I constructed a RIPS complex. I ran the algebraic computations to get the persistent homology. And persistent homology is typically represented with a persistence diagram. This is what we have on the right. And every point like this point or those points over here, it represents a topological feature in a given dimension. So over here, we are looking at dimension 1 features. And the x-coordinate of this point is the radii in which we see this topological feature for the first time. Oftentimes, we call it the birth time. And if we take the y-coordinate of that point, oftentimes we call it the death time. It's the last radii for which we see that feature. So this single point over here, well, the x-coordinate really corresponds to a distance between two neighboring points. So this is once all those points are connected, we start to see a circle in the union of the box. And around the value of the radius 1.7, this cycle is actually glued in, so we stop seeing this. And so I did this persistent homology computation for the noiseless case, a little noisy and a very noisy data. And what we can see is that there's this point which is far away from y equals x, from the diagonal, and it really tells us that, well, the distance of this point from diagonal tells us for how long, about the range of the radii for which we see this feature. So the farther away we are from diagonal, the more prominent the feature is. And despite the fact that over here the level of noise is quite high, we still see a clear signal. We see a noise. Where the noise is coming from? Well, those configuration of points like this one over here, they may be forming a cycle which appears for some radii and disappear for a radii which is just a little larger than the initial one. And that really corresponds to the noise. But what the robustness is telling us about is, well, even if we add a considerable amount of noise, we still see a signal. We can still detect that this collection of points was sampled from a circle. And again, I'm referring back to the example we started from. So it's not only multi-scale, it is robust. Okay, and I made the introduction for simplicial complexes coming from point clouds. It's by far not the only choice we have, and we have many other choices, but I think I'll stop over here just to make sure that there are no questions. So if you have any questions about the general idea of a persistent homology, please ask them now. Okay, if there are no questions, let me take you for a little tour on the applications. And well, in order to use this machinery, you don't really need a point cloud. You can work with pixel, voxel, cubical data. You can work with time series. You can work with correlation or similarity matrices, and a lot of technology around, a lot of methodology carries over. Let me give you a few examples. Looking at the pixel voxel data, that is a project with some scientists in radiology in Imperial College London, when we are looking at the trabecular bone. And well, we are trying to provide a better diagnostic tools for osteoporosis. So what we see over here is a slice of a 3D scan of a vertebrae, right? So they take an element of a vertebrae from a human, and make a micro CT scan in this case. On the left-hand side, we have a patient with osteoporosis. On the right-hand side, we have a patient, the same gender, very similar age, no osteoporosis. As you can see, the difference between left and right, well, there's clearly a difference in the density, and that is something which is used as a gold standard in the measurement. So if you ever go to take a densitometry, they will measure the density of your bone. However, what we realize by looking at, in this case, cubical persistent homology of those three-dimensional images, is that there is also a structure which is important. And you can kind of see it over here. Over here, so this is a trabecula, or spongy bone, or kość beleczkowa in Polish, if you wish. So those cycles in spongy bone, they are kind of thin and large, and over here they are thick and small. This is something persistent homology is capturing. And it seems that we are capturing much more information with this, looking at the structure than looking at the density. So that's one example where we can use a persistent homology of a cubical complexes. That's my very naive illustration of a time series, but topology can also be applied to time series analysis. And there are different ways you can do it. You can actually do a lower star filtration. So look at the inverse image of this function from -infinity to some constant, and then this constant, and manipulate this constant and see what is the topology of the set you obtain. You can also go into, for instance, Takens embedding theorem and try to do a reconstruction of the dynamics. And that's so this is an illustration from a paper by Yuri Katz and Marian Gidia, where they look at the economical time series, more precisely about the S&P 500. And they look at certain topological measures of those time series obtained by a technique which, swapping some details under the rack, I may say that this is a time delay embedding. Now, what they realize is that when this time delay embedding became more cyclic, so over here in red, we have this S&P 500 time series. This is roughly 1990, 30 years ago. This is roughly right now. And we see a few major crashes. I think this is 2001, .com. This is 2008. We have something towards 2012 as well. And this point cloud start to become more, which the point cloud which we obtain by using sliding window embedding seems to become more cyclic, or there is more one-dimensional persistent homology once we are approaching crashes. That's kind of naive explanation. What kind of what we are trying to show right now is that the market is getting into more chaotic regime before crashing, and then that's really uh, an attempt of using topology towards dynamical systems, so stochastic dynamical systems, and try to draw some conclusions about important economical indicators like economical time series. Okay, let me stay with economy for a bit longer, because over here I have correlation matrices. What we are looking at is a correlations between 24 major commodities in the US market. And again, those are weekly time series. So we are looking at the last 30, 40 years. And for every point in time, yes, question? Okay. For every point in time, we kind of have a fixed correlation matrix in which we are measuring a correlation between those 24 different commodities. And we see how it changes as we progress, again, from 1990s to the present time. And what we can realize is that, that there are clearly 4 different regimes, which again they are divided by the major crashes. And looking at the changes in these correlation patterns between commodities or prices of the commodities, they are determined by crashes. Something we can detect with topology. But if we really believe that there is some dynamics behind the market prices, the commodities prices, then this dynamics is moving from one regime into another once we are passing, through the major crisis, and that's something we can detect with persistent homology, looking at the correlation matrices. Okay, let me step up from finance and economics. Let me speak a little bit about material science. And over here, we are looking at databases of potential materials. Those are vast databases containing millions of so-called hypothetical materials, which potentially can be generated. And some materials are good for some applications, and some of them are not. Well, there are various ways we can figure out if for a given application we may have in mind, think about CO2 capture, for instance, which material is the best. The problem is that checking this using some sort of quantum simulations, typically quantum Monte Carlo simulation, takes a huge amount of time. So it's not possible. It is not possible to do it for the whole database. What we are doing over here instead is we are looking at the descriptor of a shape of a material. So in this case, those are porous materials, those are zeolites. We sample collection of points uniformly from the pores of these materials. We put balls over there of the radius R, we let R grow. We get our persistence diagrams, well, that is just an equivalent representation. And what we can argue is that materials which have similar shapes, they have similar properties. So if you have a good material, then a material with a similar shape will also be good. If you have a bad material, then material with similar shape of pores will also be bad. And that observation allows us to cut a lot of computations while actually going through the databases of those hypothetical materials. Again, that's cutting long story very, very short. Let me mention one more example in which methods of topology have a very nice non-empty intersection with rigorous numerics, interval arithmetic, in which, well, we can use techniques of rigorous numerics, in this case interval arithmetic, to compute homology or a persistent homology of a sublevel set of continuous functions in a mathematically rigorous way. Well, what do I mean by that? Well, if the partial algorithm, which we have over here, terminates, it means that we essentially have a proof that the output is correct. So not only we can work with a point cloud, if you give me a formula, an algebraic formula in a space which is not too high dimensional, And you ask me, okay, Pavel, what is the homology of the sublevel set at x equal 5? Then in principle, I'm able to answer this question using a computer. Of course, implementation is a big thing in topological data analysis. We are working on various efficient implementations. And one software package I'm personally involved in is Goodies, originating from INRIA. Let me mention this important thing. So TDA can be not only can be, but should be interfaced with various methods in standard statistics and machine learning. And how we are doing this? Well, our gadget is a persistent diagram. It's a collection of points in R2, where the x coordinates again corresponds to for a fixed point. Well, every fixed point corresponds to a topological feature. And the x coordinate of that point corresponds to the radius in which we first see the feature, and the y coordinate corresponds to a radius in which we see that feature for the last time. So we have a collection of points in R2. Well, this is not an ideal output for statistics for machine learning. It has a variable size. So we need to polish it a little bit into what we call the persistence representations. And there are various persistence representations, various ways of embed that thing into, for instance, a Hilbert space. Some of them are better, some of them are worse. The question about embedding, coarse embeddings, that there are also very important theoretical questions. And but once we have an embedding into a Banach space or Hilbert space, then we can think about using this topological information to make a statistical inference, to do a hypothesis testing, to compute confidence intervals, and many, many more. And again, going through the persistence representations is a big topic by itself, so I won't touch it. I'm just putting a flag that it is over there. But let me kind of argue about one thing. So I strongly believe that topology and statistics, they really need to go together. I'll just give you two very classical examples. One of them is this Anscombe's quartet. It's just a collection of points in a plane which have exactly or almost exactly the same descriptive statistics. So if you take mean value at x or mean value at y, standard deviations along any axis, for all those four collection of points, you will get almost exactly the same number. So looking at the standard descriptive statistics, you won't be able to tell those collection of points apart. Again, what makes them different is the shape. And the motivation of this original work by Anscombe is that, well, you shouldn't only look at the statistics, you should also visualize your data set. And the point is that you can visualize your data set if you are in low dimension. If you are in high dimension, that became impossible. And this is precisely where I believe topology can drop in and help. So Anscombe's quartet is a classical example. There's more recent example, which is called the Datasaurus dataset. Again, the same story. We have a collection of different point clouds, which have almost exactly the same descriptive statistics up to the third digit of accuracy, but their shape is drastically different. You can move from two concentric circles, collection of lines, going all the way to this tyrannosaur, I believe. Right. So again, it is important to understand shape, and that's something that's something that topology can bring into a statistical methods, and that's why I believe statistics and topology should go hand to hand. So here are some resources. I will be more than happy to share the slides later. You can essentially click on each of them and get the link to a little bit more information about persistent homology. Okay, any questions about persistent homology? Because for the last 10, 15 minutes, or however much I'm left, I would like to tell you a little bit more about mapper algorithms. Okay, so persistent homology gives you this gadget persistence diagram to describe a shape. Um, However, from the perspective of persistent homology, this data set on the left and the data set on the right, they're kind of the same. Well, if you think about it topologically, then we can actually retract all those flares over here back to the main cycle. And well, the main bulk of the persistent homology will not change. Oftentimes, however, it is important to have those flares. And mapper algorithm is an attempt to capture them and visualize them in a certain way. So let me start with a general mathematical concept which underlies the mapper graph. That's called a rep graph. So essentially, if we have a manifold M, which in this case is a torus, and a function f going from this manifold into real numbers, in this case it will be just a z coordinate of a point, then we can define a rep graph. I think I have a definition over here. So we have our manifold, a function. We define an equivalence relation. So we'll say that x is related to y if, well, the value of our function is the same. But not only that, x and y have to belong to the same connected component of the fiber. Right, so let's take a look. So for instance, if we take a z value somewhere over here, then the inverse image is just a circle. So there's one connected component. So the second point of the definition don't change much. However, if we take a point over here, take an inverse image, then in the inverse image, we'll have one cycle over here and another cycle right in here. So we'll have two connected components. And the rep graph is just a quotient of our manifold by this relation with the induced homology, with induced topology, and that, well, if f is a Morse function, that ends up to be a graph, which is the rep graph of this manifold and the function. Okay, so that's a standard concept from mathematics from late 40s of the 20th century. The mapper algorithm is essentially the same construction with one difference. And the difference is, well, we don't know our manifold M. We just know it from a finite sample. The rest remains exactly the same. So we have a finite sample of our manifold. We have a function from that sample into real number. And right now I want to define a relation. It won't be an equivalence relation anymore. So 2 points are in the relation if their values are close. So f of x is close to f of y. And well, I cannot say that they belong to the same connected component because everything is discrete right now. But instead of speaking about connected components, I will be speaking about clusters. And introducing a clustering analysis is a huge different topic, but in essence, let me actually look at the example. So what I'm doing over here, I have this collection of points sampled from my torus, and 2 points will be close if they will be mapped to the same element of a cover of a real line. So in other words, I pick a cover, kind of arbitrary, and well, if 2 points end up to be mapped by our function f in the same element of cover, then I'll consider them close. And then what I'm doing is I'm looking at the inverse images of the cover elements. So for instance, inverse image of that element will be this collection of points. And you know what a clustering algorithm should tell us in this case is that, well, probably they're coming from one chunk. The case where we'll have two chunks will be an inverse image of this interval, and once we have some points over here as well as some points over there. So, you know, informally, a definition of, we can define a cluster by saying that, well, elements within the cluster are close to each other and they are far away from the elements of a different cluster. And now, once we take the clusters which we obtain from inverse image of the intervals, well, we'll have one cluster over here, perhaps still one cluster over there, but definitely two clusters for the inverse image of that interval. We just carry on going down. Then I want to define for you a mapper graph. And this mapper graph is essentially an abstract graph having vertices corresponding to clusters and edges between vertices corresponding to non-empty intersections between clusters. So for instance, we have that edge over here, and it's here because the cluster coming from an inverse image of this interval, the cluster coming from an inverse image of that interval, they do have a non-empty intersection. And this non-empty intersection is really a reason why we have that edge. So trying to wrap up the mapper construction, well, there are a few knobs we need to adjust. So we have a cover of a line, we have this function mapping our points into real line. We need to understand how we want to cluster things. And well, oftentimes it's not easy to choose them all. But that algorithm turns out to be extremely, extremely useful in many applications. Let me name one of them. So this is a work by Gunnar Carlson, Monica Nicolau, and co-authors, in which they took a breast cancer data set. They took a breast cancer data set, they performed certain operations on them, and then they built this mapper graph. And there's one more thing over here. So we can have different functions on those points. So we can use one function to construct the mapper graph, but then we can have another function that allows us to define certain coloration on the vertices of that graph. For instance, and okay, how to define this coloration? Well, just take a cluster and compute an average value of a function. So they choose certain quite complicated function to get this Y-shaped data set. However, and they understood that the structure is kind of Y, a letter Y. This is a breast cancer data set. So what they wanted to do is to understand survival. It turns out that, well, those are people without cancer. There is 80% of the cancer patients are over here, including some heavy cancers towards the end. But that part was kind of not known before to go to the community. So those are also patients which have cancer. But there is something unique that about this group, which is the survival rate. So survival rate in this group is essentially 100%, unlike in that group, especially over here, which is very low. So the survival rate may be this additional function that we can use. And I realized that I'm running out of time. The question is, do you want me to go for another 5 to 10 minutes, or should we stop right now? I totally leave the decision up to you.
Basically, there is no limits, strict limits, I mean. So please go ahead.
Okay, so I'll try to wrap it up in the next 10 minutes. Thank you, and I do apologize for taking too much time on speaking about the persistence. Okay, so look, so mapper algorithm is a big thing in topological data analysis. And if you ask somebody from outside mathematics about TDA, about topological data analysis, they will speak about mapper. And actually, Gunnar has created back in 2009 or 10 a company in Silicon Valley called IASD. It's a big company, roughly 100 employees, which is using this technique in to analyze different data sets. However, the problem which I was trying to mention over here is that there are quite a lot of knobs to adjust: cover of the line, lens function, clustering algorithm. Quite often, it's not easy to choose them all. And that's why I want to present to you an alternative, which is very simple and very geometrical in nature. That alternative was proposed by me. Call it a ball mapper algorithm. And instead of giving you just a sequence of instruction how to obtain it, let me present to you how to construct it on this collection of points, which again have a shape Y. Don't ask me why. So what I'm doing is I'm choosing an epsilon net. And those are those colorful points. And an epsilon net is just a subset of my initial point cloud, having the property that For every point in my initial point cloud, there is a colored points, not far, one of the colored points, not farther away than epsilon, um, from any point. You can formulate it in Hausdorff in terms of Hausdorff distance, but essentially what is happening over here is that, well, if I put a ball of a radius epsilon centered in the points from our epsilon net, or the colored points over here, well, this collection of balls will cover my whole point cloud. And then, well, if you are a topologist, it should be enough for me to say that I'm taking one-dimensional nerve of that cover, but let me be more precise. So what I'm doing is I'm again building an abstract graph, and the vertices of this graph will correspond to these colored points, or the points from the epsilon net, and the edges will correspond to non-empty intersection of the balls. For instance, this ball over here, that ball over there, they do have a non-empty intersection, and because of that, I will put this edge. So eventually, I'll get a graph like this to represent my point cloud, and again, it contains some information. We know that there is a heavy center, plus free flares, free outliers going away. And if I would be looking at some data, I would say that the center is a normal state, and those outliers, those flares represent some anomaly state of some sort. So if you are into R, I encourage you to take a look at my R package, and essentially you can play with this construction. Before we play with this, I would have another quiz question for you. Just to, it's a sanity test for the method, but also a fun thing to really see that it's working. So we'll be dealing with this object, which is a lucky cat. If you like Chinatowns and Chinese food, you probably saw a lot of them. And the idea is we put a lucky cat somewhere in the table in the middle, and we are walking around this cat with a camera. We are taking pictures. So over here, we are just taking a front face picture of a cat, and then you see it appearing in a different angle. Over here, we see a back of a cat, and then we are continue, and we are coming back to a front of a cat. Each of the pictures we took is a gray level picture, so no colors. Essentially, it's a very low resolution picture. It's 128 by 128. So something extremely low resolution for nowadays standard picture. But what I will do, I won't do any image analysis. I will just, take the first row of that image, followed by the second, followed by the third row, etc., etc. And by doing so, I will vectorize this matrix of numbers into one long 16,384 dimensional vector. So every image will correspond to a point in 16,000 something dimensional space. Right? And we have a number of images. So we have a point cloud in this 16,384 dimensional space. And once we have a point cloud, and since we are speaking about TDA, you probably know what is the next question. What is the shape of this point cloud? And that's another quiz question. So I'll give you 10 or 20 seconds before I give you an answer, but please feel free to unmute yourself and try to guess. Okay, I'll give you a hint. So starting over here, we have a point in this high dimensional space. While we are moving on the trajectory over here, we are moving away from a point. We are moving away. We are very far right now when we see the back of the cat. And then we are getting closer back to the point, but we are not backtracking. We are getting back closer on another trajectory. So we start at the point, we move away, and then we come back using a different route.
It has one-dimensional first homology, probably.
Precisely, yes. So it has one-dimensional first homology. We can detect it with a persistence. It is something like a cycle if we have actually a continuous parametrization. If we run it to a ball mapper graph, we'll get something like this, right? So we clearly see a cycle. We see something more though. right? So the points over here are much more connected. They're much more like each other than the points on the top. And can you give me an interpretation by looking at the pictures why it is the case? Now the trick is I can cheat. So in the software, I can just click on the vertex and it will tell me which images it's coming from. Oops. So the back of the cat is much more uniform than the front of the cat. If we actually look at where the data are coming from, this is the front of the cat, that's the back of the cat. So the back of the cat is much more alike. So I really need to move by a large angle to see a considerable difference. Again, that's something we can see from very, very pragmatic analysis. And once we have this tool, which kind of not only tell us about the regions of the point cloud in high dimensional space, but also about the neighborhoods, and this is really given by the edges, then we can go ahead and start playing with very different data sets. And again, I could speak for a very, very long time about that. If you are interested, there is this UC Irvine, University of California, Irvine, very famous data set with a lot of data to play with. For instance, you can do it using persistent homology or a ball mapper. Well, in that case, we not only have a structure, which is a cycle again. In this case, there's again the Y shape, but we also have a coloration. And this data set is coming from a banknote authentication. So long story short, there are fake banknotes, there are the true banknotes. For each of them is characterized by 13 variables. So essentially every banknote corresponds to a point in 13-dimensional space. And if we plot a ball mapper graph, it will be in the shape of Y. But then every vertex from this graph corresponds to a ball in the 13-dimensional space. And I can ask how many banknotes in this ball are fake and how many of them are real. And the blues are fake, the red are real. Well, what we can see quite immediately is that we have kind of two different families of fake banknotes. And indeed, if you look at this link and the resources, if you read through a paper, you will realize that they use two different printers to fake the banknotes, which is precisely what we see over there. And that's the type of analysis you can do with that type of methodology. Okay, I'll skip Brexit, but that's another interesting application of mathematics in political sciences, trying to understand why Brexit happened, or why Trump 2016 election happened to be concluded in the way that it was concluded, and why, despite all the election polls giving, for instance, a very clear victory to Joe Biden recently, why this victory was not that very clear. Again, this machinery can be used to understand this type of data. I'll skip that part because after this talk, well, you may or probably you should get an impression that topological data analysis is something that mathematics can give to the people outside mathematics, but it is partial misconception, because I strongly believe that rigorous tools of data science can be used inside mathematics as well. Let me just give you one example, which is a joint project with Radmila Sazdanovic and my PhD student, David Gurnari. We are looking at knots, the space of knots, not properties. Again, I won't formally define what a knot is. You probably know that. But knots are complicated objects to deal with, right? It's an embedding of S1 into R3, quotient by relation of isotopies. So what people have done is to assign different knot polynomials to a knot. Classical Alexander polynomials, more recent Jones, even more recent Humfly PT polynomial with a Polish accent over here. And those are polynomials that describes knot structure. So for instance, I can take a Jones polynomial for all the knots up to 15 crossings, right? So that the knot diagram can be drawn with no more than 15 crossings. And then, well, I will see that all the Jones polynomial, they kind of span 32 possible coefficients. So what do I mean? Well, if I restrict to nodes up to 15 crossings, that there will be, a0 plus a1 times x plus a31 times x to the power 31. So in total, those polynomials, by just looking at the coefficients, directly translate into a collection of points in 32-dimensional space, where again, the coordinate at x to the power I is just the ith coordinate of my point. So I can take all the nodes up to 15 crossings, and I think that there is something like 250,000 of them, and see how they look like. Well, this is how they look like. And there are different things knot theorists care about. For instance, the number of crossings. Over here, blue means 15 crossings. So we see that the peripheral nodes, the one which are the farthest away, they are of the maximal number of crossings, and we have lower number of crossings as we move towards the center of the structure. Well, they do care if the nodes are alternating or non-alternating. And as far as I remember, the non-alternating nodes also occupy the peripheries of the structure, while the alternating nodes sit inside. But they also care about that's actually a mistake. It should be the knot signature. So they do care about the knot signature. And what we see over here is that there are different regions. Different colors represent different signatures. There are essentially 0, 1, 2, 0, 2, 4, 6, and 8. So different colors represent different signatures. And what we can see from that plot is that nodes of different signatures have Jones polynomials that live in different regions of this 32-dimensional space. And so Radmila is trying to wrap it up in certain hypotheses in the knot theory about whether Jones polynomial can recognize signature in certain cases. But again, that's something that can be inspired by looking at the methods of topological data analysis. And finally, let me put some functionality on the top of it. So, I really like knot theory because we have a fixed data set. There are knots, and we have a number of invariants. So the three different polynomials I mentioned to you is just an example of much larger collection of variables that we can put on the top of it. And the question is, well, the question we can ask is, well, how Alexander and Jones polynomials are related. Well, here's the Alexander polynomial for also nodes up to 15 crossings. We have alternating nodes inside, non-alternating nodes in the middle. Also, looking at the number of crossings, the peripheries are occupied by the highest number of crossings. The center is occupied by the lowest number of crossings. The things that is most interested to my colleagues in knot theory, the signature seems to be much more mixed over here than in case of Jones polynomial. So the obvious hypothesis, which we can get by looking at the data, is that Jones recognize more than Alexander polynomial in terms of the signature. But we can also construct a mapping by essentially mapping one graph to another graph. And again, I won't be going into details of the technique, but we can just take all the nodes which are covered over here in this mapper graph of Alexander polynomial and see where they are located in the Jones polynomial space. Well, here they are. And once we are moving forward, then I can take the next part of the sausage and map it back to the Jones, and I will get a bunch of nodes over here. And it turns out that once I move from right to left in the space of Alexander polynomial, I am moving kind of in a similar way through the space of Jones polynomials. So in other words, the space of Alexander polynomial seems to be just a space of Jones polynomial compressed in this direction, in this y equals x direction. Again, it's a very vague hypothesis, but it gives a tool to compare different invariants of objects that are of interests, not only outside mathematics, but also inside the mathematics. Okay, so here are some resources about Mapper. Again, I will be more than happy to share the slides later. But let me try to wrap up. So again, the credo is about shape, and shape is important. And in my opinion, methods of topology, topological data analysis should be used alongside the methods of statistics in order to understand shape. Again, we are not and we should not be restricted only to persistent homology and Mapper. We are constantly looking at new ideas from mathematics that we can actually use to describe discrete data. And that's why I kind of would like to invite you to the topic, because there is an enormous amount of fantastic idea in mathematics that can be used in data science, in biology, in medicine, even in to understand the space of knots in the knot theory. And that's something we are trying to do in applied and computational topology. This is something we are trying to do in the Dioscuri Center at IMPAN. So I'll be very happy to be able to talk to you and take you to this journey together. And that's why, I would like to warmly invite you to applied and computational topology. Thank you very much for your time, and I'm very sorry for going 20 minutes over the time.
Thank you very much. Now we can start our QA part of our meeting. Are there any questions to the speaker? Please do not hesitate.
You were mentioning cubical data. What do you mean by cubical data?
Okay. So let me stop. Let me actually stop sharing. Let me close recording.